All right, here is part 2 of lesson 10.1.4. My favorite problem in this lesson, maybe my favorite problem we've done so far. Just 6 short problems, 6 sub-problems of all the different kind of relationships we've done. Big ones that are going to come through here, things like angle measure, inscribed angles, central angles. We have tangent, we have diameters. We were going to see it all through here. I have it split up into each problem has its own slide so I can work on it and use the space I need. But make sure that you understand every step of the way that I'm taking here, why I'm saying, like why I can use inscribed angles and arc measures, and how I can use those to figure out central angles and so forth. Some stuff was from 10.1.1, some stuff was from 10.1.2, and some stuff on here was from 10.1.3 and today. So let's start with the first one. First one actually has to do with what we were doing today. So they're saying PQ is a tangent line to C at point P. And so we have a tangent line PQ. It is tangent because it only intersects at that one point, point P. And it says if PQ, this line, this segment right here, is 5 and CQ is 6, then let's find the length of CP and the measure of the angle C up here. And so the first thing I'm going to do is I'm going to say, well, I know that PQ is 5. I know that CQ is 6. And from what we were talking about earlier in this lesson, if you have a radius go out to a tangent line, that forms a 90-degree angle. All right, so now I have a right triangle. I know 2 of the 3 sides. I can find the last side by using the Pythagorean theorem. And so CP is a leg of the triangle, so I'm going to say that that's a squared. PQ is a leg of the triangle, and so I'm going to say a squared plus b squared, which is 5 squared, equals my hypotenuse squared, which is 6 squared. And I know 6 is the hypotenuse because if P down here is my right angle, the hypotenuse is always across from my right angle. If I work this out now, I get a squared plus 5 squared. 5 squared is 25. And 6 squared is 36. I then can subtract over here and I can get a squared equals 11. And that a, to get rid of a square, you always got a square root. And so a, because that will go away, a equals the square root of 11. That square root is 11 as a decimal. I believe it's approximately about 3.3, but I'm okay with the square root of 11 there too. All right, to keep moving, the next part we wanted to find the measure of angle C. Well, because this is still a right triangle, and we're looking for an angle now, we can actually use inverse trigonometry. And if C is the angle I'm looking for right there, then 5 is opposite of it, and 6 is still the hypotenuse. And so I can find that measure of angle C by using the inverse sign. Inverse sign, again, because 5 is opposite and 6 is hypotenuse. Opposite hypotenuse tells me it's sine. When you're looking for an angle, that tells me inverse sine. And so we're going to do sine inverse of my opposite, which I believe is 5, over my hypotenuse, which is 6. And whatever that gives me is the angle that I'm looking for. I got to use my calculator here. And so I get the sine, I click the inverse button, so I get inverse sine of 5 divided by 6, and that gives me a 56.4 degree angle right there. And that's the end of that problem. Again, what we learned today is the only reason I could do that problem. I learned that I can get a right angle here, and once I know that's a right angle, I can use the Pythagorean theorem, and I can use inverse trigonometry. Going on to the next one, a very good one. In circle H, the measure of dr, so the measure of dr in here is 40 degrees. The measure of GOR, so that major arc G, I use my cursor, GOR, that major arc right there is 210 degrees. And now we want to find what GD is. Well, GD is the only thing that we don't know, so we know that there's 360 degrees in the total circle. We know that 210 of that's already taken from GOR, and 40 degrees of that is already taken from DR. And so like now we have gotten rid of GOR, we got rid of DR, so now we're just left with GD, which is what we want. And what we get here, I'm again going to use my calculator just so I don't screw up. 360 minus 210 minus 40 gives me 110 degrees, which is my answer for the measure of GD. So I'm going to write it like they do. Measure of GD equals 110 degrees. Okay. The next part is we want to find the measure of OR. Well, the nice thing about this problem is that we know that GOR, that major arc is 210. So they have 210 degrees in GOR. And another nice thing about this problem is that they tell you that GO here, or maybe they don't tell you, but you can tell that GO here is a diameter, which means this measure here from G to O is 180 degrees. Because if you have a diameter, it cuts your circle perfectly in half, which means the measure here must be 180. And so what we see then is that GOR is 210 and G to O is 180. And so what we can do is we can take the whole 210, we can subtract away the 180, and we'll just be left with 30 degrees. And that 30 degrees is just that OR part. And so I have my measure of OR, and it's 30 degrees. Again, really what happened there was, if I put it in red, GOR, that full part is 210. G to O was 180 because of the diameter. I just subtracted away. I subtracted away this part right here, and I was just left with OR. The last part here, the measure of RGO, R to G to O, and that's pretty easy because there's 360 degrees in the entire circle. Oh, they're looking for this angle RGO. Okay. Sorry, they're looking for this inscribed angle down here, RGO, not a measure, not an arc measure. And that one's not too bad either because we know RO is 30 degrees. We just said that down here. RO is 30 degrees. And the inscribed angle that creates that arc measure is always half the length. Because remember, we talked about this, I think, in 10.1.2. The central angle is always the same as your arc measure, and the inscribed angle is always half of what your arc measure is. And so if that arc measure is 30, that angle measure, what is that, RGO? RGO is half of that angle measure, so it's 15 degrees. And those are my answers here for that problem. And that one here. All right. Next one here for C. It might take me more than one video here, but I do like to take my time on these ones because there's a lot that goes on. AC is a diameter. AC is a diameter of the circle, E. And BC and ED are parallel to one another. It wants us to find the arc measure of CD. Well, what I'm going to do actually is I'm going to find this. My goal is to find what that measure is right there because that central angle is the same as the arc measure. We've talked about that before earlier in chapter 10. What I'm going to notice here is that I'm going to erase this quick so I can see it. If this is 90 degrees right here, and AC is a diameter, which means it's a straight line, that means this over here is also 90 degrees. All right, because we have a supplementary relationship there with that straight line. And then what else I notice is that if that's 90 degrees, EB, that line EB right here, is the same as line EC because they're both radiuses of the same circle. And so EB and EC are the same, which makes this actually an isosceles right triangle. And if this is an isosceles right triangle, that means this is 90, this is 45, and this is 45. We have a 45, 45, 90 triangle. Well, we can now use the fact that this line right here, that red line right there, represents 45 degrees. Well, we have these parallel lines here. We have this parallel, and I'm going to try to put it here again. We have these parallel lines here, which makes these two angles, and I'm going to put them in blue now. This 45 degree angle and this angle up here are the same. And they're the same because those are alternate interior angles. So that means that not only is angle C down here 45, that means angle E up here is 45 degrees, which means that this arc measure, CD, measure of CD, that arc, is equal to 45 degrees. So kind of a lot of things. I do it kind of quickly. I first said that that was 90 degrees because this is a supplementary relationship. I then realized that this is an isosceles triangle because EB and EC are the same. If this is an isosceles right triangle, that means that was 90, 45, 45. And then I used that 45 degree angle and the fact that that is a transversal cutting parallel lines, that's 45, that must also be 45 due to the fact that's alternate interior. And then I just said, well, if the central angle is 45 and that central angle creates measure CD, that means CD must also be 45. All right, keep moving along here. We have intersecting chords. We did a problem like this last week. I don't remember if it was Wednesday or Thursday. But what we see here is that we have HJ and we have HJ and KI intersecting one another. They say that HG, so from H to G is 9 units, from G to J is 8 units, and from G to K is 6 units. All right. Well, what we did with intersecting chords is we realized that if they create the same arc, they have the same angle. So what we did when we did this problem last week is we said we turn this into two triangles by connecting these points right here and here, and this point like right here to here. And then we said, well, they have an angle-angle relationship, which means they're similar. So we actually end up using triangle similarity here, which means what we can do is find our zoom factor and use our zoom factor to find that missing piece that we don't know. What this needs to be seen, though, is that angle H here is creating this arc measure over here, and angle K is creating that same arc measure. So angle K and angle H have to lay on top of each other for similar triangles, which means really the corresponding sides here are HG and GK. So what I'm going to do is I'm going to take HG and I'm going to divide it by GK to get my zoom factor here. And if I do that, I get 9 divided by 6, which gives me a zoom factor, I'll call it ZF, a zoom factor of 1.5. So if I want to go from the small triangle to the big triangle, I have to multiply my side lengths by 1.5. If HG and GK are similar, that means, or corresponding, that means GJ and GI are going to be corresponding. So I'm going to take the small side, GJ. I'm going to take GJ. I'm going to multiply that by 1.5, and that's going to give me GI. And so if I do that, what I get is GJ is really a length of 8. 8 times 1.5 gives me an answer of 12. And that's just using similar triangles and the fact that when you have intersecting chords, you actually get similar triangles. All right, move on to the next one here. I'll be close to finishing this one. It looks like I'm going to put this one and the next one in a second video because this one takes a little bit of explaining.